Hi there. Today we'll look at BigBird, Transformers for Longer Sequences by Manil Zair and Garuganesh et al. Of Google Research. So this paper on a high level proposes to replace the quadratic attention mechanism in transformers by a mix of random attention, windowed attention, and selective global attention, therefore achieving a complexity of linear memory requirement instead of quadratic memory requirement. And as a result of that, they can process longer sequences than traditional transformers like BERT and achieve better results in some NLP tasks, and they also evaluate on genomics tasks. So we'll go through this paper look a bit at the proof, because they give a theoretical kind of guarantee that their random attention mechanism can still be Turing complete and can still achieve the same things as a full attention mechanism, but we'll also look at the drawbacks. I sort of have mixed feelings about this paper, and I think I'll voice my concerns as we go through here. But first, let's look at the paper, let's look at the architecture, and I think this is actually a pretty cool paper for the empirical progression of the field to process longer sequences with transformers. As always, if you like content like this, feel free to share it around, leave a like, and tell me in the comments what you think about the paper and about what I think. Whatever, you just go nuts. All right, so the basic premise right here is that the transformers, they've been pretty impactful, especially in NLP. So they say transformer-based models such as BERT have been one of the most successful deep learning models for NLP. Unfortunately, one of their core limitations is the quadratic dependency, mainly in terms of memory, on the sequence length due to their full attention mechanism. So really briefly, the full attention mechanism, and I've done numerous videos about attention mechanism, BERT, attention is all you need, and so on. So if you want a detailed explanation of what that is, just go look up the corresponding videos. But briefly, what you'll have in NLP is a set of tokens, a sequence of tokens as an input, and you want to transform them layer after layer into sort of a higher order representation of that same sequence. And for that, you build these layers out of nodes, and you have as many nodes usually as you have tokens in the sequence. And the next set of, so each token is represented by a vector at the beginning, and each layer transforms this sequence, as I said, into sort of a higher level representation. So you want the vector of this token right here to be a better representation than the vector was right here, and you do that by incorporating information from all the other tokens into that particular vector. Now, as I said, this is called an attention mechanism, and we don't actually have to go into how it works right here, but you can see pretty clearly that if you want to do this for every token, you need to have information routed from every token to every token, like from here to here, from here to here, and so on. And this is just one token, and then you need to do it for this token, and for this token, and for this token. So what you'll ultimately get, if n is your sequence length, you'll get some n squared amount of computation and memory requirements for this. So this is a problem, and usually this means that this sequence length in BERT, this is limited to something like 512 tokens, which is okay for some applications, but if you want to summarize entire articles, entire books even, or do question answering with lots of context, it's not really enough. So people have been thinking about how to scale this input, how to scale this, and of course the main culprit is this quadratic attention mechanism, because if you double the 512, you need 4 times the amount of compute and memory. So how does this paper go about reducing that quadratic dependency? The goal right here is, of course, to get this to some O of n, right? Because then, as we double the input length, we simply need to double the compute requirements, and that would be fantastic. And that's what this paper does, and it does so without sacrificing the properties of the transformer. So here's the architecture that BigBird proposes. By the way, BigBird, another character from Sesame Street, I guess will continue the naming here after Elmo and Bert. You know, I'm waiting for the model that's the count. Yeah, that's gonna be a fun model. But so BigBird basically has 3 different types of attention, and here these are adjacency matrices in this attention mechanism. So here is the input layer, and the output layer is right here. So that basically means that node I right here would be connected, well, sorry, that's not a straight line, would be connected to this particular node and also to this particular node. So we're now trying, if we have node I right here, we're now trying to not connect it to all of these nodes, but we'll say we'll just select some at random and then connect it to that. Okay, this is what we call random attention. And you can pretty clearly see if you connect each of the I nodes to r equals 2 to 2 random nodes, then you don't have an n squared anymore, but you'll have like an O of r times n, which, you know, if r is a constant, is an O of n attention mechanism. Okay, so the main goal between the random attention mechanism is that for each query, basically, you select random tokens that you attend to, and that random number is a fixed number that's not dependent on the sequence length. And the paper is a little bit unclear about whether or not those random ones are the same for every sequence or are switched up, or are the same for every layer or are switched up, but they formulate all of this as sort of a graph, in sort of a random graph. So they formulate the attention mechanism in form of a graph. So if we transform all of these nodes into a graph, a full attention mechanism would mean that each node is connected to each of the other nodes, right? Fully connected graph. Maybe that's it. So that would be a full attention mechanism. And then they say, well, if we just have random connections between these things, then there are some theorems from graph theory that say that each random walk in this graph is going to, so this graph is going to mix pretty quickly. So I can get from each node to each other node by a random walk in a logarithmic time. And this random walk, which basically means that you go from here to here, this would be one layer of the transformer. And then if you want to go from here to here, you would have to do that in the next layer. So this formulation as a random graph leads me to believe that layer after layer, the random attention pattern is going to be the same. But also the formulation of the paper leads me to believe that this random attention differs from sequence to sequence. So I believe what's happening is that they, get a new sequence, then they decide on this pattern right here once, and then they use this layer after layer, the same pattern again. So you can see that in the traditional attention, information can basically flow from each of the nodes to each other node in one single step, right? Because each node is connected to each other node. You see this in the graph right here. However, if we only select a subset, then it needs to, if I want to go from, as I said, from here to here, then I need to do it in 2 steps, and therefore I need 2 layers. And that's going to be the culprit of this method here. And while it is mentioned in the paper, it's sort of, I feel, at least that's my my assessment of this paper, it's kind of swept under the rug a little bit. I mean, they do have a theorem that clearly says we can construct an example of a task that in the full attention setting can be solved with a single step, so a single layer, that in our random attention setting needs a lot of layers, so a lot of steps. But the rest of the paper is sort of shaky on this thing. But nevertheless, you can see how the random attention can, if you have enough layers, do the same information routing as the full attention. Okay? However, this is not a property of the random attention. And we'll see this in the next thing right here. So the next ingredient that this paper uses is window attention. And you can see over here that BigBird is ultimately going to be a combination of the three types of attention, which we are looking at here. So window attention basically means that each token at the ith position is going to attend to itself, of course. So here is I, but it is also going to attend to its neighbors. So here is I minus 1 and here is I plus 1. And this is a, this is a window size W that is a parameter, but also it is a constant, and therefore you again go from n squared to W times n, which is O of n if W is a constant. And this might be familiar to you because we've already seen this in the long-former paper. So I've made a video, or I think even 2 videos, on the long-former, which used exactly the window attention in combination with the global attention. And if you want to know more about that, go watch these videos. But the new thing in BigBird right here is this addition of the random attention. Again, the window here has exactly the same properties as the random attention. So you have, instead of a fully connected graph, you have a sparsely connected graph. Now, if you have random attention, the sparsely connected graph is like the one on the right. But if you have a windowed attention, it is kind of not randomly connected, but each node is connected to its neighbors like this. And you can also see that if I want to go from this node to this node right here, I can't do it in one step, but I can do it in 2 steps. Right? I go here and I go here. So in the terms of the attention layers, if I want to go from node 1 to node 3, I have to do it in 2 steps because each node is only connected to its neighbors. So the connection patterns would sort of look like this. So I have to go from 1 to 2, and then in the next layer from 2 to 3. So the paper basically makes up for the lack of full attention by adding layers. And you also might recognize this from a convolution operation. Like this basically, because it is a convolution operation, right? In a convolution, each node only aggregates input from its neighbors for the next layer. And then we know that as we go up the layers, the de facto window that each node looks at is going to be like a cone, kind of like this. So this is very similar to how a convolutional neural network works. And the reasoning is very similar because the reasoning is, well, in a sentence, the most important words for any given word are probably going to be its neighbors, like the words around it. And as you go up the layers, you branch out more and more, but ultimately this neighborhood principle holds in NLP as well. So again, we already saw this in the long-former, but that's the reason behind the window attention, and that's the second ingredient. And then the third ingredient is this global attention. Now, the global attention is selected tokens that are so important, and that's fixed by the developers, that are so important that they are connected to everything else. So, for example, in these transformers, you often have what's this kind of CLS token. So this is a special token that you prepend to some piece of text, and the output of this token is going to be your classification output, because you don't want to bind your classification if you need to classify the entire sequence. You don't want to bind that decision to one particular word. What you want to do is you want to have an extra token, and that's this CLS token, that kind of aggregates information from all of this. So layer after layer, you'll have, so if we go here, layer after layer, we have this one special node. And in each step, every single other node is able to send information, right here, to this node and receive information from this node. Okay, so now as a result of this, as you may be able to see, every single path is kind of maximum length of 2, because if I want to go from any node to any other node, I can simply, send information to this global node, and then the global node in the next step can send information to whatever other node. And that is a property that they use in their proof, that this attention mechanism is as powerful as the classic full attention mechanism. And we'll go through that in 1 second. But first, I hope this was clear that this combination of random attention, window attention, and global attention is what is called BigBird. Okay? They have some engineering tricks that go along with this, but in concept, you can imagine BigBird being longformer plus these random attention right here. And, as an engineer, as an NLP engineer, that makes kind of total sense. I totally believe that the introduction, the addition of these random attention patterns can absolutely help your classification or whatever your NLP tasks, because more attention, better. And I also am completely willing to believe that using the full attention matrix, while it is of course more accurate, it won't hurt too much to leave some of that attention away, because essentially all the path lengths are just becoming 2, or even with the random attention are really short, are logarithmic, to route information from a node to some other node. So the loss that you incur is kind of in a logarithmic scale in terms of performance, while the gain that you make is sort of in a quadratic or like a linear scale. You go from quadratic to linear. And that seems to me like a good empirical trade-off. All right. However, the proofs here, the proof of how these things are constructed are a little bit, I don't know. So what they do in the proof that this function can is a universal approximator. People have already shown that full attention mechanisms are universal approximators. So they show here that this sparse attention mechanism is also a universal approximator. They make big use of star graphs. What they say is, okay, if we have a star graph, which is one node connected right here to every other node, this is a star graph. If we have a star graph, we can achieve the same thing than with a full graph. A full graph is where every node is connected to every other node. But as I already said, what they need for this is multiple layers of this star graph. So, and that has to do with the fact that if I want to route information, I basically have to go via this middle node right here. And there's an additional complication, because this middle node, in our case right here, is only one node. I can't route information at the same time, like I can't have this routing right here at the same time that I have this routing right here, like going from here to here, because I only have one middle node. And this is not how this is very dumb math, but maybe you have to imagine that there is one memory slot, and you can only use that one memory slot at the same time for one of these things. So essentially, what you'll have to do is you'll have to do the green thing first, and then in the next step, you'll have to do the blue thing second. And then, so these are now pairwise routing between nodes. But ultimately what an attention mechanism does is it does everything to everything, right? In a single layer, it routes information from all the nodes to all the other nodes. And to achieve that, so you need multiple rounds of this. And it turns out that in the worst case, you actually need n rounds of this. So, you trade off, you go from n squared to n memory and compute requirements in a single layer. But in the worst case, you need n layers to recover the power of the full transformer, and that is the last one of their theoretical results right here. So first they prove universal approximations, and second they prove Turing completeness. These two properties have been proven for full attention mechanisms. And third, they prove that there are tasks where you actually do need n layers to solve them with their limited attention. So, you know, I'm not sure, but I feel you can make any sort of polynomial algorithm into a linear algorithm like this. Like I have like a cool sorting algorithm, right? So if this is my sequence that I want to sort, what I can do is I can simply, take a random subset of them, like this, and this, and then kind of go and sort them, and then put them, like I send them to the global memory like this. I sort them, and then I put them back, right? And if I do this for enough rounds, okay, if I do this for enough rounds, at the worst case, I need n rounds to sort my, or log n rounds if I do it smartly. But, in, the single step here is, just O of n. So I have now an O of n sorting algorithm. I have my sort of a bit of worry to express things like that. And but it is, from an empirical standpoint, I absolutely believe that this is enough. Now, my second quarrel right here is that if you look at the proof, first of all, what it makes use is this star graph. And the star graph corresponds to the global attention. So that's not much to do with the random attention, though they use the random attention in their proof, but I at least believe that it would be possible with the global attention only. And then the second thing is, if you look at the parameters that they use for the experiments, and I've already said this in the long-former video. So in the long-former video, it turned out that if you look at how big this window attention is, it turns out that you're still, the original BERT attended to 512 tokens, and then you look at the window, and the window was still 512 tokens. It's just that the global attention was even more. So ultimately, they ended up using more memory than the original BERT. And here, if I look at the parameters of their thing, and they have multiple experiments right here, and I believe this is the base version. So this is the base version. They also have this large version, but here this is the 12-layer version, and you can see they have this block length, and we'll get into the block length in 1 second. But then you can see that their window size is 3 times the block length. The number of random tokens is 3 times the block length, and the number of global tokens is 2 times the block length. So that results in 8 times B. So 8 times 64 is, can I calculate this? Or am I stupid? It's 512, yes. I actually calculated this before. So this is 512 tokens. So, you go from BERT that has 512 tokens and attends to 512 tokens to also attending to 512 tokens. Of course, the advantage here is that they now have 4,096 sequence length. So they have the freedom to not attend to as many tokens as they have in the input length. But, to put it in perspective, this here uses more memory and more compute on its face than BERT, because BERT attends to as many tokens but has a smaller input sequence. And, there's sort of a thing where in order to make these sparse attention things work, you have to go pretty high in the number of things you attend to. You can leave away some, but it's not like you can, scale up orders of magnitude of your input sequence length. So that's this promise of linear attention is sort of, it's kind of fulfilled, but not there yet. The second thing I would like to point out is that in a lot of cases, the number of random tokens is actually set to 0. So really making use, I believe, of these of the global of the number of global tokens. So that seems a bit strange in that they continuously refer to their random attention mechanism, but then in a lot of experiments they don't actually have a random attention mechanism. I believe they have to do that because that's kind of what makes them different from the long former in principle. But still, yeah. So the last novelty, let's say, is an engineering novelty in that they now always consider not single, for example, they don't consider single random attention. They always consider these in blocks. And that's because our current hardware is really bad at sparse stuff. Really bad at single indexing, gathering single things. So if you can do everything in blocks, you basically get these blocks almost for free. So it takes only marginally longer to retrieve this full 2x2 block right here than it would to retrieve the single instance right here. Of course, that means you have, 4 times, you still use 4 times more memory, but it is not 4 times slower than the original thing. So you can use these blocks right here. You can do it for the random attention. You can do it for the window attention, as you can see here. So you break this window pattern a little bit into blocks, and that makes it a lot faster, or that speeds up. You get the speed up almost for free. And then they make another approximation in that the way they do this windowing is, and let's just go really briefly. So you can see right here that it would be very cumbersome to gather. So what we need, we're just going to focus at this dotted thing right here is a bit confusing. So you want to attend to these things, and these you can just get out with a matrix slice, really easy. But then you want to attend to this kind of blocky thing right here from the window attention, right? Like this thing. And this is hard to get out because you'd have to kind of index each row individually, and that's very slow. So what they do, there is this matrix roll operation where you can sort of roll the axis around. So what you'll do is you'll take this thing right here and you put it to the left right here, and you'll take, for example, this thing right here and you'll put it to the right, or no, like it's up and down, but in essence that's what you do. And you can fold all of this blue stuff into a rectangular matrix, if you can see right here. So you kind of roll this back, roll this back, roll this forward, and you replace whatever is missing by these. Now this again gives you some inaccuracies because this block right here was never intended to be attended to, and all of a sudden you see you have the K6 in here. So it gives you a bit of inaccuracies at the edges of the sequence, but you can take that, you can take that hit for the increased performance that you gain by now having a rectangular matrix. TPUs are really efficient at this, not as efficient at this. And then the only thing that's really slow is gathering these random blocks right here. But also by having the same amount of random blocks per input token, what you'll do is you'll end up with just one of these columns right here, or R of these columns. And that again gives you a rectangular matrix. So this thing right here you can process very, very efficiently using a TPU. And the mistakes you make are basically this thing right here and this thing right here, because those weren't intended and are at the edges of the sequence. So these were the tricks of BigBird. To quickly summarize, BigBird is basically taking a transformer, saying, well, why do we need all of this attention all of this full attention. Maybe we only need some of that and can already do a good job, especially considering the attention mechanism goes over multiple layers. So we don't need a routing from each token to each token. We can make up for not having a fully connected graph by simply running multiple layers. So their sparsity is, first of all, you have this random attention, which I believe changes from sequence to sequence, but stays within or among the layers of the same sequence. Then you have the window attention with the reasoning. So the reasoning behind the random attention is that if you have a randomly connected graph, the path lengths are on average logarithmic. So you can route information efficiently. The reasoning behind the window attention is that probably neighbor information is very important, and that has been shown empirically. And then the global attention, the reasoning behind this is that some of the tokens that are fixed by the developers are so important that it's very beneficial that each other node is connected to them and that they are connected to each other node. The result of that is the BigBird attention mechanism, which is basically longformer, which already had these two, plus the random attention. This achieves a linear complexity in terms of memory and compute, though linear has to be qualified a bit because it's modified by the window size, by the number of random attention tokens, by the number of global tokens, and in practice often ends up being fairly large-ish. And also the theoretical guarantees now come with the fact that you need multiple layers. In the worst case, you need sequence length amount of layers, which in the worst case would result right back into a quadratic requirement for memory and compute. They do some engineering tricks right here, and their results are pretty good. So the results in various tasks, and we'll look at some of the tasks right here. So these are def set results using base size models, for example, where you can see they do outperform basic Roberta models. They outperform longformer, which may mean that the random attention is useful, but in these things it's also always may just mean that you've thrown more compute at it. At least I'm not really looking that they outperform the models, because as you can see right here, if they compare to state of the art, and granted these are models that have been trained specifically for these tasks and are crafted and engineered, and BigBird manages to hold itself against them in a lot of tasks and even gets state of the art on some. What I'm more interested in is that it can reach good numbers. It doesn't necessarily have to be state of the art, but it can reach good numbers, which tells me that probably the empirical hit that I take by not having the full attention is justifiable by the speed up and memory savings I do get. Especially when you see results mixed like this, sometimes the other model is good and sometimes the BigBird is good on different variations and so on. I would not make a big deal out of the fact that it is state of the art. I get that the authors have to do that. I would do so as well, but don't think that this is the best thing now. It's very probable they just thrown also a lot of compute at it. What is cool is they do some genomics experiments. So not only do they have NLP state of the art, but also they go into genomics and experiment with data there. Don't want to go into that because ultimately it's another task, and I believe the paper is about the architecture. All right, so that was BigBird. I hope you enjoyed this video and I learned something, certainly. If you want to check out the proofs, they're actually pretty entertaining to read. And I'll see you next time. Bye-bye.